All right, welcome back again, everybody. Today we're going to be doing section 11.3, which is all about the integral test and estimates of sums, or I should say estimates of some sums. Let me go ahead and pull up the slides and we'll get started right away. Oop, there we go. All right, 11.3. So here's the overview. We're going to get some motivation for this thing called the integral test. We're going to develop the test, get the statement of the test. Then we're going to prove a very, very important test called the p-test. And then we'll talk about how you can use the integral test to estimate the sum of a series. One thing I'll say, just to kind of build off of what I was saying in the last section, we're going to be getting a lot of theorems in this chapter, many theorems. And so each section is basically going to be learning about a new theorem or a handful of theorems. We're going to get a bunch in today's section. We're going to get a bunch in the next section, 11.4. And then 11.5 is using a bunch of them. Being comfortable with the results of the theorems is important, but you don't need to have the theorems memorized. You just have to be able to use them consistently and correctly. So we're going to get a couple more today. Let's get started. So this is what I was going to mention in the last lecture too. Generally speaking, it is difficult to find the exact sum of a series. Uh, a lot of times just trying to figure out what these things add up to is really hard. So when you've got a series that is nice, like a geometric series, or I should say, when you've got a series like a geometric series and you've got a formula for what it adds up to, that's really nice because you don't really have that in general. And so a lot of times what you're really concerned about is just convergence and divergence. You want to know just if a series even converges at all. And then you talk about, okay, what does it converge to? So this is a great example. Think about this series right here. This is the series of the sum of the reciprocal squares, right? So you do n squared, so you get 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. You might be curious about what it adds up to, or if it even adds up to anything at all. Does it converge or diverge? So it turns out there's no simple formula for the partial sums of this basic series, but it was proven it was proven long ago that the series does converge. And in fact, we're going to prove that it converges today. And we're going to view a more general result actually when we look at p series and the p-tests, p-tests. Um, but Euler actually proved that this series converged to this number, pi squared over 6. So this thing converges to pi squared over 6, but he didn't prove it until 90 years after the problem was first posed. So that means that we knew this series converged for 90 years before somebody was able to show what it actually converged to. What's the moral of the story? Generally speaking, it is difficult to find the exact sum of a series. So it's nice if we can at least prove if it converges at all. That's the big question. Does it even converge at all? If it does, then we can start to address the issue of what it converges to. A little side note, this is actually, this sum is actually a particular case of the infamous Riemann zeta function. The Riemann zeta function is this function. It's defined as this series, and the variable of this function is the exponent s. And in this case, s is a complex number. Remember, every real number is a complex number, so this also holds for real numbers, and this is actually the case when s is equal to 2. So, oh, by the way, this is the Greek letter zeta. That's why it's called the zeta function. Frankly, a lot of my research involves zeta functions. So, like my dissertation result was I constructed a zeta function that worked really nicely. I'll just say it like that, a zeta function that gives us a lot of information. But yeah, if you change the exponent, it changes the results of this convergence. It may converge, it may not converge. So any mathematician or any math major, I strongly encourage you to follow this link to the Wikipedia page and just read about the Riemann zeta function. The Riemann zeta function is related to the Riemann hypothesis, which is basically the most famous unsolved math problem right now, uh, which basically says that the critical zeros of this function all lie on the line with a real part equal to 1/2. So if you can prove that, you've proved the Riemann hypothesis and you'll be world famous at that point. So read up about it. We can talk more about it later if you're interested, but this series is just one special case of this more general function, which is kind of cool. All right, so let's develop the integral test. We're going to develop this test in the next several slides. We can use our knowledge of improper integrals to help us determine the convergence or divergence of some series whose terms are positive. So it's kind of like if you think back to improper integrals, we're going to use what we know about them to talk about some series. So as an example, let's consider this curve and this series, the one we were just looking at, zeta of 2, you could say. Um, Now, the graph of y equals 1 over x squared looks like this. Okay, I'm going to go to this slide. And if you look at these rectangles underneath the curve, the area of each one of these rectangles is equal to one of the terms in this series. So here the area is 1 over 1 squared, which is right here. Here the area is 1 over 2 squared, right? It's basically just looking at the area. So the area here, the width here is 1, 1, 1, 1, but the height is given, or it's given by this point, right? So the height here is going to be 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. And so you're talking about the area of these rectangles altogether. So each one of these rectangles gives you the value of one of these terms, right? That's the idea. And so that can help us get an idea because we know about this curve and we know about its improper integral. So maybe we can use that result from a previous result or a previous section to give us information about this series. Okay. Yeah, so if we exclude this rectangle, then the sum of all the remaining rectangles here must be less than the area under the curve 1 over x squared. That's just a simple geometric argument, right? So the sum of all these areas has to be less than the area under the total curve. That's what this is saying. There we go. So that gives us basically, that gives us an upper bound in some sense. It gives us an upper bound. So we know by the p-test for integrals that the area under that curve is finite and the area happens to be equal to 1. So the area under this curve, all of it, is equal to 1. All right, that's an upper bound for this sum in this case. All right, so that means that, okay, there you go. The partial sums of this series must be less than 1 plus that. Oh, I'm sorry. So our upper bound is actually 2. Sorry, I neglected the first rectangle. So an upper bound for that series is 2. So whatever that series sums up to, well, for one, it's convergent. It's convergent because it sums up to something less than this, and this is equal to 2. Is that what I say here? Yeah, there you go. Yeah, there you go. So the partial sums are strictly increasing as well, and we know they're bounded above. So by the monotone convergence theorem, they must converge, and so our series must converge by definition. So this was giving us the boundedness, and that this whole geometric result was giving us the boundedness. It's also bounded below by 0, I should say. Bounded below by 0. It's got to be greater than 0. And it's strictly increasing. So the strictly increasing part is happening because at each step, we're adding a positive number. We're adding a number that is strictly positive. So as we keep adding these positive numbers, the partial sums will increase at every step. They're strictly increasing. Strictly increasing, bounded above and below. Monotone convergence theorem must converge. All right, now let's tweak things a little bit. Let's look at a different type of bound. Let's look at the curve 1 over square root of x. Now, we could do a similar geometric argument with like the rectangles. So look at these rectangles instead. Okay, just like so. And the area of these rectangles is given, or is equivalent to the terms of this series, are equivalent to the terms of this series. So here's 1 over root 1, here's 1 over root 2, here's 1 over root 3, and then altogether you're looking at this series. Now, because of this geometric argument, we can see how we're getting these values and we can compare it to what we know about the integral, the area under this curve in general. So that's what I'm going to go here. The sum of the areas of the rectangles has to be greater than the area under the curve because these rectangles are overshooting the area, right? And we know that by the p-test for integrals, the area under the curve from, I should say, from 1 to infinity diverges. So the area under this curve from 1 to infinity is infinity. And the the partial sums of our series are going to diverge because these areas are actually greater at each step. So now we know that our series diverges. So the moral of the story here is that we can use what we know about improper integrals and their convergence to get insight into series and if they converge. In a very similar sense, this is like doing a real variable extension and then being like, oh, what happens when we have a real variable function? What does that do? What does the integral look like? And so on. And then it's like, okay, well, now we can use that to get information about the series itself. Okay. And so all of that culminates in this, which is what we call the integral test. So the integral test is a theorem, and just like any theorem, it's got a list of hypotheses that must be satisfied before you can get the conclusion. And so here they are. We're going to suppose several things here. Suppose f is a continuous, positive, decreasing function on this interval, and suppose that the terms of this sequence agree with that function on the positive integers. Okay? So in essence, these kinds of pictures. That's really what it is. But you need continuous positive decreasing to use these results. Now, here's what we know. If the improper integral of that function from 1 to infinity is convergent, then the series is also convergent. Additionally, if we know that the improper integral of that function is divergent, then the series must be divergent. And that's what we get. So what is the utility here? Excuse me. The utility is, hey, if you've got a series where the sequence terms look kind of like a function that you could play with easily using an integral, you might be able to use the integral test. The catch with this test is you need all these conditions. You need a lot of conditions to use this test. Continuity, positivity, and decreasing. So you have to show that those are true before, not even that, you got to show these things are true, and you've got to show this before you get this result about the series that you're interested in. All right, that's the idea. Um, oh yeah, so some notes about this particular test. When you're using this test, it is not necessary that the series begins at n equals 1, nor is it necessary that the integral begins at x equals 1. What is important is that the function f is eventually decreasing. So in other words, there needs to be a point where that function f is decreasing from then on out. From then on out. This is related to what I say at the bottom here. If you remember what I mentioned in the last lecture, when we're talking about convergence and divergence, a finite number of terms does not affect that. So what we really care about is the tail of the series and the tail of the integral, you could say. All right, so you don't need to start at 1. It doesn't really matter where you start. All that matters is what's happening by the end. So um, this sums it up well right here. So if you're looking at a truncated series where the index starts at some other number n, and you find that this series is convergent, it asserts as well that the series here, when you start at 1, is convergent. Because if you add a finite number of terms to something, you're not going to make it suddenly explode. That's the idea. Okay, so just remember, we care about the tail end, not any finite number of things. All right. Okay, now let's talk about a very, very important type of series known as a p-series. And then we're going to develop the p-test for series. We did the p-test for integrals. It's going to look very, very similar. Now we're going to do the p-test for series. So a series of this form is called a p-series. So for example, every value of the Riemann zeta function is given as a p-series. That's what it is. But those values may not exist because that depends on if the series converges or not. So if the series doesn't converge, then, for example, the Riemann zeta function is not defined at that number. or it has an asymptote at that number, or so on, right? So that's what a p series is. 1 over n to the p, where p is some power. And then this is the p-test. And this is an amazing test. We're going to use it all the time. The p-test says if your p series, or sorry, the p-test says this p series is convergent if p is greater than 1, and it's divergent otherwise. That's it. That's it. It's convergent if p is greater than 1. So if this is p equals 2, it converges. If it's p equals 3, it converges. If it's p equals 4, it converges. If it's p equals 1.00000001, it converges. As long as p is greater than 1, it converges. That's what's beautiful about it. And then what's funny enough is if p is equal to 1, then we get the harmonic series. And if we have the harmonic series, we showed that that diverges in the previous lesson, right? So that diverges. Okay. Now, what I'm going to do is I'm going to prove this theorem. I'm going to prove the results of this test. But I'll say that I'm going to give you a more direct proof. So if you look at the proof in the book, the proof actually uses the p-test for integrals to prove the p-test for series, which is totally valid. And you can use the integral test to your advantage and use the p-test for integrals. But I think it's a little more fun to not have to rely on an integral to prove something about a series like this. So I'm going to give you a more direct proof that a colleague of mine shared with me a while ago. It's also got a lot of good techniques in it, so I want to go through it. So we're going to do something similar to what we did for proving that the harmonic series diverges. We're going to look at some partial sums. In particular, we're going to look at this partial sum. This is the clever part. So we're going to look at the partial sums of this form, s sub 2n plus 1. And I'm going to write out what that is. So s sub 2n plus 1 is the partial sum when you add up all the terms to 2n plus 1. So here's what it looks like. 1 plus 1 over 2p, 1 over 3p, 1 over 4p, dot, 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 1 over 2np, 1 over 2n plus 1p. That's this, the 2n plus 1th partial sum. Now we're going to kind of group these things together and notice a pattern. So we're going to be able to re-express this series in a different way. So I'm going to pair things off, and check this out. Pair this off, or maybe I'll do it up here. Pair these, pair the ones in between, and pair these. And when you do that, you get this. Okay? Now, the reason that I wanted to do this is because we can now express this series in a different way, starting at 1, but having a different final term, you could say. So this, or sorry, I should say, this is equal to this series right here. And this is one of those times where you should ponder this and think about it for a minute. So what I want you to do is look at this sum here and make sense of why this can be written like this using sigma notation. So ponder that for just a minute. Okay. All right. So hopefully you can see why we're getting this result. But now here's the other cool thing. Remember, we're dealing with inequalities, and we just want to talk about convergence or divergence, so inequalities are very helpful. This result here is strictly less than this result here. And the reason is that here, notice the 2i plus 1 was changed to a 2i. Well, 2i plus 1 in the denominator is going to give you a smaller number. It's going to give you a smaller number because the denominator is larger. So by writing this as 2i, we're going to get a larger number. And that's why we get this, right? In other words, this thing is less than this thing. That's the basic argument there. But now we have two identical terms. So we can rewrite this sum as 2 over 2i to the p. All right, there we go. So now we've gotten that s sub 2n plus 1 is less than this. And now we're going to tweak some things a bit. All right. So pulling what I just said, that's what I was just saying a moment ago, this, okay? There's some things we can do here. So for one, we can pull out some stuff. Notice that we've got a 2 and we've got a 2 to the p in here. Those don't depend on I, so we can pull those constant multiples out of the series. And that's what this is. Okay, what I'm doing right here is writing 2 over 2 to the p. Oops, back up. 2 to the p is 2 to the 1 minus p. That's what we're pulling out of the series. Okay, now we're left with this series. But this is the cute part. This is one of the reasons I like this result. This is just the nth partial sum of the p series. This is just the nth partial sum. So we can write it as s sub n. So altogether, we get s sub 2n plus 1 is less than 1 plus 2 to the 1 minus p times sn, right? Cute. Next, again, we're working with inequalities here. We can also say that the nth partial sum has to be strictly less than the 2n plus 1th partial sum. So we can replace this with this and get another inequality. Why is this handy? Because now we have an inequality that's got the same factor on both sides, so we can move those pieces to the same side and factor it out, factor the common factor out. So take this and add it to this side, and then factor out s sub 2n plus 1, and you get this. That's it right there. Now we can divide both sides by this result, divide both sides by 1 minus 2 to the 1 minus p, and we get this. All right, so the 2n plus 1th partial sum is strictly less than this number for any p, for now. Now, for p greater than 1, it follows that this thing is greater than 0. So basically, if p is greater than 1, then this result is greater than 0. And so that means that s sub 2n plus 1 is a strictly increasing sequence. It's a strictly increasing sequence. And it's strictly increasing and it's bounded above. So by the monotone convergence theorem, we know that this sequence converges. In particular, the sequence of these partial sums converges. Or in other words, the p-series converges. So this limit is equal to this limit, which is equal to this series, and we know that this is going to converge by the MCT. Therefore, the p-series converges as long as p is greater than 1. There you go. Okay, so this is one of those situations where this is a little bit more, this proof is a little bit more pure, you could say, than the one that's in the book, but it is a little bit more complicated. Oh, I just realized I've had the thinker on the whole time. There we go. Good thing to ponder then. Good thing to think about as I'm talking about it. So there we go. That's the proof of the p-test. So long story short, a p-series converges if p is greater than 1. Okay. All right. Now, perfect. Okay. So now let's talk about how to estimate the sum of some of these series. We've been using integrals to determine convergence. The related integral doesn't give the exact value of the convergent series. So this is one thing to keep in mind. This is related to what I said at the beginning as well. Using the integral test does not give us the sum of the series. It just tells us if the series converges or not. So how can we use this to get a little bit more information about the actual sum of the series? That would be nice. That's what this is going to do. It's going to let us estimate the sum. So yeah, here we go. An integral might give you a pretty good approximation because we know that the terms of our series always lie on the curve of that related function. So the integral might give us a good estimation, but how good is that estimation? What we could see from the pictures earlier is that we were doing basically a left or a right endpoint approximation. But now our integrals are improper. That's not something that we looked at before when we did our left endpoint and right endpoint approximations. So here's the question, what's the error? What's the error involved? If we're going to do, if we're going to do, where is it? This. If we're going to do like a right endpoint approximation, what error is involved? All right. So to talk about this error, we usually call it a remainder. So in this context, the error that's produced when you approximate a sum by an integral is called the remainder. And this makes sense because we're talking about discrete sums in this case. We're talking about discrete sums, so we call it a remainder. So suppose we've got a convergent series, and let's look at the partial sums. Partial sums when you chop it off at n. Since the series converges, we can say that the sum is the limit of the partial sums. Now, the sum itself can be written as a partial sum plus some more, plus a remainder. That's what's going on here. So the sum itself can be written as a partial sum plus some remainder. And the remainder is basically the tail end. The remainder is the tail end of the series. So what is the remainder? The remainder is the difference between the actual sum and the partial sum. And the remainder depends on where you cut. It depends on the actual value n. It depends on where you chop the terms off. That's the idea. So the remainder is this difference, okay? Now, if we refer back to this picture like I did a moment ago, when you do a right endpoint approximation like this, what you find is that the remainder, the tail end of the series, has got to be less than this integral. It's got to be less than that integral because, again, it's like it's like chopping it off right here. And what we're saying is that the rest has got to be less than or equal to the area under that curve. Okay, I'll throw the thinker back up now. It's been on there for too long, but I'll throw it on there again now. Think about that for a minute, and then we'll talk more about it in a second. All right. Okay, so the tail end of the series has to be less than this integral, less than that integral. Again, this is all assuming that you've satisfied the hypotheses of the integral test. That's one thing I got to emphasize. This only works when the series that you're investigating satisfy the hypotheses of the integral test. All right. Same thing over here. I didn't switch the picture up, but if you did a left endpoint approximation with, I think I did 1 over root x previously. If you did a left endpoint approximation, then what would happen is the remainder, oops, wait, come back. The remainder would be greater than this integral, the integral from n plus 1 to infinity, because in this case you would be overshooting. So I guess on the picture it would look like this. Let's see, right here, oops, right here, and so on. And so the remainder would be like what you get if you chop, right here. Chop it off right there. And so what you know is that the rest, the rest of the area of those rectangles has got to be greater than the area under that curve. And that's how that works. That's how we're getting the estimate. So putting it all together, we can get the remainder estimate for the integral test. So suppose that your function satisfies all of the hypotheses for the integral test, then also suppose that your series is convergent. Then if we write the remainder like we did earlier as the actual sum minus the partial sum, then you get this upper and lower bound for the remainder. So the remainder, the tail of the series, has to be bounded below by this, and it's got to be bounded above by this, which is really, really handy. So the remainder is between those two integrals. This also gives us an estimate for the sum itself, because again, the remainder is the difference between the sum and the partial sums. So if you replace r sub n with s minus Sn, you get this. And then if you add Sn to both sides, you get this result right here. So if you want to know what a bound is for your actual sum, the sum of your series, it's going to be the nth partial sum plus this integral for a lower bound, or it'll be the nth partial sum plus this integral for an upper bound. All right, now let's use it. So that's the integral test. I'm sorry, the remainder estimate for the integral test. Let's use it here. Let's look again at the Riemann zeta function evaluated at 2. So when we evaluate it at 2, we get this series. We know that this series converges. It converges because of what I said at the beginning, but also it converges by the p-test. By the p-test. Wait, do I say that again in here? Where do I say that? I just said it right now. So this converges by the p-test because here we have p, we have p equals 2, which is greater than 1, so this converges. What does it converge to? Well, Euler proved that it converged to pi squared over 6, but let's just get an approximation. Let's just get an approximation. Let's approximate the sum of the series using the first 10 terms. That's the first question. So compute the first 10 terms and just give an approximation for what the series converges to. Then let's ask, what's the greatest possible error involved in that approximation, right? So if we're going to chop off the series after 10 terms, how much of an error does that produce? I want to know that. And then let's go one step further and let's ask ourselves the real question, which is, how many terms do we need? How many terms are required to guarantee that our sum is within a tolerance of, say, 0.0005? So basically, I want my approximation to be accurate to 3 decimal places. How many terms of the series do I need to guarantee that? All right, here we go. So first, S sub 10, you can produce it just by writing out all the terms and adding them up. If you plug this into a calculator, you'll get that it's approximately this number, approximately 1.549676. So that's our 10th partial sum. So that's an approximation. What is the error involved? So in this case, the related function is 1 over x squared. And what we can do is we can use the remainder estimate for the integral test. Why? Well, this function happens to satisfy all those hypotheses. So it's continuous, it's positive, it's decreasing, and we know that our series converges, so we are actually allowed to use that remainder estimate. All right? You have to verify those hypotheses first. If this is not true for your function or your series, you cannot use this test. All right. Now, for any n greater than 1, we can look at this integral right here. This is an easy integral to anti-differentiate, or an easy function to anti-differentiate. We can use FTC2, and we get this. So this improper integral is this limit. Here's the antiderivative of 1 over x squared. We're going to evaluate it from n to t, which means we get this limit. And as t goes to infinity, this term disappears, and you're left with 1 over n. So this integral is equal to 1 over n. Nice. All right. Why do we need that integral? Because that's going to give us our bound. So using the integral test, the remainder estimate for the integral test, we know that the remainder associated with the 10th partial sum has to be less than this integral, and we showed that this integral is going to be 1/10. There we go. So altogether, this says that the tail associated, that the size of the tail associated with the 10th partial sum has to be smaller than 1/10. So this is actually not a great result. This is not a good, this is telling us that our approximation is not very good, because this is saying that the error could be as big as 1/10. That's really what it's saying. The remainder or the error could be as big as 1/10. So we don't even have accuracy to 1 decimal place. Not a very good estimate, right? And we calculated this using just S sub 10, and the exact value of the sum is closer to this number. Pi squared over 6 is about that number. And you can see when you compare these two, the error begins in the first decimal place. This is 0.5 and this is 0.6. So not a very good estimate. In other words, 10 terms are just not enough. 10 terms are not enough if you want a good estimate. That's where the next question comes in. How many terms do we need to actually get an approximation that's within a tolerance of 0.0005? So in other words, what n do we need such that r of n, or r sub n, is less than this number? That's what we're trying to figure out. So using the remainder estimate, we know that r sub n is less than this integral, which we calculated to be 1 over n. So what we need is we need 1 over n to be less than 0.0005. Solve that for n, and you get this. Okay, this is a telling result. This is a telling result because this is saying that you would need 2,000 terms to get an estimate that is within 0.0005. Wild. 2,000 terms just to have accuracy to 3 decimal places, or I should say just to guarantee accuracy to that many decimal places. You might have accuracy before that point, but you would need 2,000 terms at least to guarantee that accuracy. All right. Okay, so that's a bit of a hefty result, and it's a lot of stuff to think about. But on that note, let's play. All right. If you've got more questions about this, you can ask me during the activity sections. Um, the next section we're going to get some more theorems. We're actually going to get the comparison tests. The comparison tests are really, really nice. We will talk more about remainder estimates later on as well. Let me think for a minute. Which section is it? Oh man, I can't remember what section it is. We'll talk more about remainders and estimates and tail ends of series as we go on. But I'll stop there. Thank you all again, and I'll see you next time.